All right. Thank you for coming to our talk, hosted by the Computer Science Club at the University of Waterloo. First, I'd like to thank people who helped make this talk possible. It was funded by the Math Endowment Fund. We had a bunch of people helping us, from Professor Michael Terry and Waterloo AV, who got us the equipment. From the School of Computer Science, we had Vic DeCiccio and Debbie Mustin really doing a lot of work to get transportation and everything going. And finally, I'd like to thank our lecturer for coming here, because he did take a time out of his schedule from the conference for C++ 09 in Toronto. So, if you would all give a hand for someone who I don't need to introduce, because I'm sure you've all either worked with it in CS246, or you've seen it around the industry, because it kind of just swept over a lot of things. So I would like to thank Mr. Bjarne Stroustroup.
Thank you very much, and thank you for inviting me. Yes, they did sort of Shanghai me from the standards meeting that's taking place in IBM in Toronto at Markham. So I'm going to give you some idea about what the next generation of C++ is going to be. And after that, I'll take questions on that and anything else that you sort of feel like asking about. And I made this talk partly on the way back from the previous standards meeting, which was in Oxford. Gave me an excuse for having a photograph on my slides. Usually you'll see my style is the boring black and white with code. What am I going to do? I'm going to tell you a little bit about what C++ OX is supposed to be, what are our aims, how do we go about standardizing a language, why do we standardize a language, what are the design rules of thumb that we need, and then I'm going to concentrate on just two language features. There's just no way of doing a laundry list of features well. It's boring. You can do it yourself. So I'm just going to show two features that illustrate some aspects of the language as it'll be, and then you can ask questions. Now, sometimes people say, why on earth are you interested in standardization? Why working on a next generation of C++? I mean, people think everybody's going to write everything in Ruby or whatever the next fad is. And if you believe that, you can go and look at the applications list on my home pages that has a few, very, very few C++ applications, which basically the message is it's everywhere. And so as an illustration of everywhere, here's one of my favorite pictures. It's a picture of Mars. It's taken by one of the Mars rovers almost 3 years ago. That's a really cool project. I mean, those Mars rovers, they had a design life of half a year, according to the engineers. They promised the managers 3 months, but they knew half a year was a limit because the dust accumulation on the solar receptors and the Martian winter would get the rovers. That was 3 years ago. Now, I think it's cool because the high-level functions on the rovers are written in C++. The scene analysis and the autonomous driving is all written in C++. You actually send them a message every day telling them what to do for the next 24 hours because transmission is difficult. Now, suddenly one day after a couple of months, the solar panels cleared. And that's how we can still have them running 3 years later. And for about 2-3 weeks, we didn't quite know what caused these solar receptors to be cleaned. And this is somebody's theory about how this was done. Later, they came up with a more boring explanation of dust devils on Mars. This will also allow me to point out that Photoshop is a C++ program, and a lot of animation work is done in C++. So there is a lot out there to work on. And so what is C++? It's a general purpose programming language. It has a bias towards systems programming. That is, you can write cool embedded systems like Mars rovers and iPods in it. And I like to be able to write device drivers and things like that in it. It's a better C in the simple sense that you can write everything you can write in C in roughly the same way, with more better type system and more notational support, and at the same speed. You can build your own types, you can build hierarchies of your types, and you can parameterize types with other types and algorithms with other algorithms and types, things like that. Note in particular, I'm not saying it's an object-oriented programming language. It was never meant to be just an object-oriented programming language. The key thing here is that these techniques work together, and quite often the best solution to the problem is a combination of these techniques. So if you need a fancy long word, which you probably do since you're in a computer science department, you can call it a multi-paradigm programming language. But what it really means is it's a set of tools that works with each other to create the best solutions in many cases. Best means easier to write, easier to read, easier to maintain, runs faster, uses less memory, all these good things. So when we work on the next standard, you have to have some overall goals. I mean, everybody has some goals for a language. These are sort of the highest level goals in the C++ OX effort. Would like to make C++ a better language for systems programming and for building libraries. So the view is that somewhere you're reasonably close to the hardware and you have to be good at that. And the way you get away from the hardware, which you want to do when you can, is to build a library that raises the level of abstraction of what you're doing. This may sound trivial because this is what C++ is and what it's reasonably good at and what made it grow. And so we're sticking to that. And we're not, for instance, trying to build the best language for high-performance computing. Or in particular, we're not trying to make the best language for medium complex applications with medium performance requirements written by mediocre programmers running on Windows. You can do very well if you specialize for either of those fields, but this is just not what we're doing. We're going for abstraction and performance, and the combination serves us well. And we would like to make C++ easier to teach and learn, and since we can't cut away things, that means that we have to increase uniformity, we have to make stronger guarantees about things. Basically, we're not as successful about that as we could be, and I'll explain to you why. The real problems we're trying to deal with simply we want people to write better programs. We want to make it easier to write code, easier to maintain, and easier to achieve acceptable resource usage. I know there's these ideas that the next Intels will execute an infinite loop in 5 minutes, and therefore you don't need performance, but lots and lots of people don't quite agree. The people that are doing sort of the Google and the Amazon of the world aren't complaining that the machines are getting too fast, and the gadgets sort of we're using, people are not complaining the processors are getting too fast, they're complaining that the battery lives aren't good enough, which is also a performance issue. So there's a lot left in resource usage terms here. And basically, all a language can do, and what we're trying to do, is to allow people to express their ideas directly in code, and in the case of C++, trying to do that without loss of efficiency. Things are easier if you could throw away the efficiency, but that's somebody else's game, not ours. And so, What's the problem? The problem actually is the popularity of C++. There's at least 3 million programmers writing C++. That's a lot of people, and we can start arguing. I'm pretty sure we don't know the real number to the nearest million. It's like if you can count that you aren't rich enough. But it's an incredibly diverse population too, in application areas and programmer abilities. How do you do something that helps groups of people you don't even know? And a lot of people want improvements. If you have any clue about C++, you'll have some ideas of what could be done better. I have some list of things that could be done better. I'll get to those. They're very long. It's anybody who comes and tells you they have a perfect language are either naive or salesman. So there's lots of wish lists. You can see some on my homepage. A couple of years ago, I was trying to get some idea of what people really wanted. So when I went to give a talk, not quite to this big an audience, but sort of 50 people and so on, say, okay, let me see, what's your favorite features? Each sent me down on a piece of paper your two top choices. And what I found was for n people handing over 2 requests each, there's about n distinct first choices. This is a very hard job. Furthermore, they always want to help people that are just like them. So if you go to a telecommunications company, you'll get everything that helps telecommunications company with trained engineers. They're not interested in novices, they're not interested in certain forms of database stuff. GUI can take a flying leap and a few other things like that. You go to a more sort of applied business thing and you get a completely different set of features. So it's really, really hard to know what to do because of the diversity here. And by the way, everybody thinks they can get a feature just like that. Hey, I mean, you can do it in C#. Just take C#'s feature. That'll work fine. No. Features do not easily graft from one language to another. I mean, you can graft an apple branch to a pear tree or something like that. But people want us to graft apple branches to a cactus or the other way around. It just doesn't work. I mean, adding a feature, it has to fit into something. And by the way, after people have asked me these n features, or by the way, the language is too big, can't you make it smaller? Oh yeah, and don't break my code. Whatever you do, don't break my code, but make it much smaller. No, it's tricky. And people do that. Even when you make the jokes, people will still do it. Even when I make the jokes, I'll still do it. Because there are these things I really, really would like. And people like stability. There are billions of lines of code out there. I've had some discussions with people about that S. I mean, can I use the plural in that? And the answer is, I'm pretty sure. This is a large number. And even good extensions can do harm. A lot of people think, well, what harm is there to give an extra feature? Well, the first and most obvious harm is that the textbooks get bigger. And to learn it, you have to know one more thing. And this is n more things. There's there's 200 people here, right? So maybe not 200 new features, but you really don't want to deal with that. Furthermore, you can't implement a language with too many features well. It takes too long. The features interfere with each other. There was an experiment done up at Microsoft last year, which is very interesting when it comes to how you can harm others accidentally by a good feature. They took a lot of applications and compiled them with and without the CLI enabled, the Common Language Infrastructure, in other words, reflection, with all the trimmings. And what they found was that when it was compiled native, it was 80% code, 20% data. And when it was compiled with metadata, it was 80% data and 20% code. And you have to remember that's about equal amount of code here. So yes, reflection can be nice, metadata can be nice, you can do interesting things with it, but do you really want to give it half or 2/3 of your memory to get it? Is there something else you could do with that memory? We just I don't know how big your memory is, but on mine, they just add more than a gigabyte. That's a lot of memory. If I have that memory, what else can I do? Like not use the disk when I'm doing an algorithm? This kind of things matter. So we have the ISO standards process, what we're doing. And so we have got a standard in 98, which is the one we are trying to work on. We had a revision in 2003, and if you can tell the difference between C++ 98 and C++ 03, you've just been reading too many manuals. It's really not for users. It's to make sure that everything is just right, so that the compiler writers don't get into trouble, incompatibilities and such. We have a library technical report. We have a performance technical report, mostly addressing embedded systems issues, and now we're working on C++ OX. And some of us are very, very keen on getting that X to be decimal. There are people that would like to sort of wait and take it easy and don't rush and don't make mistakes. There's lots of people like that, and well, if they get their way, that'll be C++ OX. Let's see, C++ OXA or something like that. So if you want to know about this, all the documents, more than you could ever possibly want to know, is on the group's website. If you can type WG21 into a search engine, you can find it all. Tons and tons of stuff. So who's doing this work? In principle, it's nations. The final votes are nations. And there was 22 members last time we voted, and we got a 22-0 vote, which is unheard of. We have between 5 and 10 at each meeting now. The American National Standards Committee is the technical host, and there's other meetings elsewhere. I don't know if the Canadians have meetings. They certainly have a delegation that turns up every time. But I was at the British meeting before the previous standards meeting, so it's not just one group, it's actually a sort of a network of standards group. There's about 160 members that sort of pop up on the electronic discussions, and about 60 at each meeting. I would say there was about 70 in Markham now, and about 200 people involved. This is a formal process. It's a slow process. It takes years to do anything. A lot of work's done under Robert's Rules of Order. It's painful. And there is such an attention to detail that it's really painful. It's also very democratic. I mean, if one of you want to, you can join up. They'll charge you $1,200 for the pleasure. It's all done by volunteers, and that's the cost of taking in. And at your third meeting, you can vote. You can vote one vote, just like Microsoft. It's fairly democratic. That means that you have to deal with big corporate interest and with single issue fanatics. There are people who will spend those $1,200 so that they can vote for their feature. The real problem in the standards committee is people who think they know everything. They really annoy those of us who know we don't. So it's a formal, it's the worst way except for all the rest. Apologies to Churchill. So why do we bother? Well, personally, I can't think of any other thing I can do with my time that has a bigger positive direct impact on a lot of people. I mean, there's 3 million programmers out there. Since they sort of turn over a decade, so over the next decade, that's quite a few million people that you can help directly, and then all of their users. Also, there's lots of techniques that you would like to get into use. And the standard academic way of getting people to change the way they do things is to give a talk. And then they expect people to change their behavior. happens very rarely. The way you get people to do things differently and hopefully better is to put some tools in their hands. Language features, library features. And the best way of doing that is to get it into the standard so that it pops up in their machines so that there's minimum barrier to trying it. And furthermore, I really hate vendor login. I mean, I started this work when I was working at Bell Labs, and we basically used every computer there was, and every operating system there was, and quite a few that you'd never heard of. And all the vendors has this trick of adding features and having slight incompatibilities to make their language not only much nicer than the other guys, but to make sure that once you're using these features, you can't move to the other platform. I'm a great fan of thin interfaces to vendor-specific things. And everybody, doesn't matter if it's Microsoft or GNU, is trying to get you use their special features to make sure you don't go to the opposition. And for C++, the ISO process is absolutely central. We don't have a rich owner that can give you some free libraries that cost $12 million to build. We don't have a marketing organization. We don't have any sort of major meetings where people come together. The only thing that's central in the C++ world is the standards committee, where people can come together. I mean, where else do you get people from Sun and Microsoft working together on some details? It's not been interrupted by anything that's happened in the last 15 years, so it works. And then finally, yeah, we've got a good standard, but that was 10 years ago. We know better now. In some cases, we knew better then, but we couldn't get it done. So let's see. What's the technical aspects of all of this? Here's a set of rules of thumb. First of all, we don't want to break your code if we can help it. And that's important because there's a lot of code and a lot of people that would get really, really annoyed. Just telling people that, well, your code is just too ugly. And that style of coding actually was, I mean, Dennis Ritchie knew better than that. It's not an argument. If I'm breaking your code, I'm breaking your code, and you're not going to like me for it. So we try very hard not to. We don't quite guarantee 100%. In particular, each time we take a keyword, we break somebody's code. So we're very careful about which keywords we pick. But apart from that, we try not to break it. There's endless discussions about whether we can break ABIs. And the point is there's so many ABIs that it's probably impossible not to break some of them. But we try quite hard not to break the major ones. We would like to prefer libraries to language extensions. That's an obvious ideal from a user's point of view. That is, if I want a facility, there's two ways a vendor, compiler, supplier, standards committee can give you that feature. You can build it as a library, say the C++ complex arithmetic library, or you can do it as a language feature, say the C built-in complex numbers, which they got 15 years later than C++, because it takes a long time to get a language feature designed and into the language and distributed, and you cannot use a feature till it's available on all of your platforms. So if you want to do complex arithmetic, you better use C++ and C, because C99 that provides the complex numbers are not universally available. It's only 8 years since they put them in the standard. With a library, you get the facilities as soon as that library will run on your machines, which is quite often. So this is an obvious ideal. The snag is that all the enthusiasts, all the fanatics want real language features. So that's a very hard ideal to follow, but we try. I would like to prefer generality to specialization. That is, if you want to add something, add a mechanism that allows people to write better libraries. Add a facility that allows people to use the hardware better. don't add a specific facility that does something for the end user. Again, good principle, works well, but people really want a real language feature. And so there's pressure for doing specialized things. Support both expert and novices, that's obvious. At any given time, most of us are novices at something or other. So we should support ourselves for starters. And our friends, who's the same way. The problem is, who's got votes in this? Experts. They tend to be real experts. But basically, when it comes down to a real choice, if you're an expert, you've spent 3 years on the committee, you've spent 10 years working for Microsoft or on the Free Software Foundation or in a national lab or something, when it really comes down and there's a choice, are you going to do something that helps the novices, or are you going to do something that helps you and your closest collaborators? It's really hard to get to the point where you can help novices. And by novices, I really mean just somebody trying something new in the language, with the language. A novice can be a really brilliant physicist. He just wants to get his work done using the language. He doesn't want to be a C++ expert. He wants to be a novice and be supported as such. Would like to increase type safety. 100% is not possible in C++, but we want to increase that, not decrease it. And we're making progress there. We want to improve performance and the ability to work directly with hardware. That's actually important, and a lot of people, this is where you get the argument, oh, nobody needs efficiency today, the machines are so fast. Only when you're in a very narrow application domain and not doing something really new and interesting. Fitting into the real world is important. Imagine I came with some language feature that really fitted into the language. It beautifully solved a problem. It's just one little problem. It doesn't fit into any of the existing compilers and tools infrastructures. So we'll solve all your language problems elegantly, but every compiler vendor has to rewrite their compiler more or less from scratch. This doesn't happen, right? So it's not just a language design problem. It's a problem in a very constrained environment. It's constrained with existing codes, existing programmers, existing tool infrastructures and such. Quite interesting puzzle. And ideally, we should make only major changes. That is, the purpose of the exercise is actually to change the way people think. If we make an individual statement in an individual line of code better, yeah, that's fine. So we get something slightly prettier. But if we can get people to write their code in different ways, thinking about what is a good program in different ways, things are really much better. That's the idea. This would be a very arrogant statement if we hadn't already done it repeatedly. I mean, when I started with C, people thought that function prototypes were unbearably complicated and dangerous and high level. I mean, nobody was writing with abstract data types, ABIs. Nobody was, I mean, people knew that object-oriented programming meant slow graphics, and it was useless to any real programmers because they couldn't afford it, and anyway, they just couldn't understand it. It's too complicated. And if you look at generic programming today, again, nobody was writing generic code. Nobody was writing sort of static compile time polymorphism, the functional techniques that comes into it. And these days you see Java and C# growing generics. So this has been done before, and we would like to do something. Again, that's a great idea, and we'll do something, but quite often there's a problem. People don't really want to argue about these big things. You come with something like I'll talk to you about later, about how to do a type system for templates. And we don't get a discussion about that. Now, if you discuss about how to write a for loop, you get a really splendid discussion. If you start arguing about whether you should have a space in between the int and the star in a pointer to int, you get a really furious discussion. People actually love discussing things that don't matter, because it's so easy to have an opinion about those things. And anyway, it doesn't matter, right? So you can discuss. Anyway, so we try to pick things. So here's something scary. There is a lot and lot of requests for new features. 14 proposals have been approved for the next C++. 14 has been approved in principle, meaning they are in the process of going through the sort of refinement process to get into the document for the final votes. I told you it was a long, slow, frustrating process. They are in the way. The ones I worry about is the active and evolution group. I'm head of the evolution group, and there was 18 proposals there. One of the great achievements here was we actually managed to cut it down to 6 on Monday. There were 7 when I left this afternoon. We'll see how many there are on Friday. My guess is that it'll be between 5 and 7. But if anything, if these active came up, we would have a major problem of how to manage, teach, implement the language. And especially these proposals that are rejected or lingering. That is, people have sort of given up. But they're good features. And then people sometimes, when I say that, it says, "You're exaggerating, Bjarne. It's not real. There's not a big problem. You just take all the good features and put them in." Well, most of these are good. And so to counter the argument that I was exaggerating, I took and looked in a directory on my file, in my file system where I keep suggestions that have been mailed to me that aren't on the lists already. So from 2006, I found 64 unique proposals that I had received that are not in this process and are not big enough to have got themselves a directory. And some of them are really stupid, and most of them are not. So there's at least 100 halfway reasonable suggestions. We cannot even take all the good proposals. Define a good proposal as something that will make life easier for 200,000 people. That's not sufficient. If we took all of those, we wouldn't be able to handle the results. So this is scary, but I'm an optimist. Still an optimist. I think we will get a manageable set of features. I think we will have thought through how they can interoperate so that we don't get sort of too many rough corners. We'll get a few, we'll screw up ever so often, but it'll be good, and it'll be significantly better than C++ OX. I've looked at a lot of code and considered what it would look like with the new features. We'll get improvements. Here's something that's scary in the opposite direction. I said we should prefer libraries over language features. And I just showed you a slide that you'd get on the order of maybe 30 new language features. You're not going to get 30 new libraries. There's 11 components from library TR, out of which is some things like hash tables and regular expressions. They're good stuff, some smart pointers, but nothing earth-shattering. We will get something that is important, namely threads and thread pools. This is all I think, because we haven't had the final votes. On the other hand, my guesses are usually reasonably good because I've spent a long time with it, and there's been preliminary discussions, there's implementations of everything I'm talking about somewhere. Not production quality, but people are testing it out. But that's not very much. There's a lot of use of the language features that have been done, because many of them are there to support libraries, and I'll show you some of that. So the standard libraries you've got will become faster and easier to use. And then I would like to see a lot more, but, well, I'm not going to get it. But people are encouraging me to believe that there will be a library TR again. which will create a well-defined set of interfaces, and implementations will become available from Boost and others so that you can use it, and that'll have some of the things I really would like. A file system manipulation so that I can deal with directories or folders, whatever you want to call it, without knowing which operating system I'm on. Date and time, networking. I really would like to have an I/O stream that I'm pumping data into and it pops out in Australia. This kind of stuff exists. It's just not standard, and it will get into the standard this way. And the library wish list has 50 plus suggestions. You can find it on my home pages, and if there's something you can contribute or would like to see, send a mail to somebody. Okay, so where are we working? We're working on machine model and concurrency. We really have to deal with these new, very weird architectures. If you've been looking at machine architectures, especially the advanced stuff, you'll see I'm not exaggerating when I'm saying it's weird. The combination of several levels of caches, of inlining, of speculation, of branch prediction, multi-cores, you name it, this is a really weird world. And we need a model for how does machine architects and compiler writers interact so that we programmers don't have to know about that stuff. That's very, very important. And then we want some support for threads. We want some atomic operations. We want thread local storage, and we want futures. That looks as if it might become available. We would like to have done something about modules and dynamically linked libraries. We basically failed. I told you everything here has been done by volunteers, and we just haven't had the critical mass of people and time to get a standardized notion of what a module is and what a dynamically linked library is. So you're back to trying to write something that will work on different systems using the native facilities. Then the thing I've been mostly associated with is support for generic programming. I'll show you some of the examples of that. But basically, generic programming is the area where there has been most movement in the way people think about things, in the way people use things, and the language is creaking in this area. They are really pushing it to the limits, and so we have to move the limits. And then there's the etc. stuff, which I don't want to go into because experience shows this is what you really, really want to argue about because it's so simple you can understand it without thinking. But that's not what's interesting in the long run. So let's look at a problem and a solution. Now, the first example I'm going to show here is initialize a list and initialization. And this is sort of, it's not computer science, computer engineering, it's sort of more like computer mechanics. This is what you get when you send your favorite programming language in for a 60,000-mile tune-up. Not rocket science. So here I would like to initialize a vector with 3 values. And so I use my favorite standard library function pushback, which is that's the function where you have a container, you have a value, you push the value into the container, and the value grows by that one value. This is the way you avoid buffer overflows because it grows automatically and there's no limit. So I do that, push 1, push 2, push 3. Now, what's wrong with this? First thing that's wrong is I said I was going to initialize a vector with 3 values. I didn't do that. I made an empty vector and I pushed in. This is verbose, right? I had to say push back 3 times. When I said I wanted to initialize the vector, I didn't say push back. Furthermore, this is 3 operations done one after the other. Very hard to optimize because I didn't do what I said. I did sort of a workaround that worked. Furthermore, you can only do that in a context where you can write a declaration followed by 3 operations. I mean, maybe I want a global vector. It's probably bad programming practice, but I could certainly not use that technique. It's not universal. So one of the ideals of the language is to express directly fundamental things you would like to do, And I would say initializing a vector with 3 elements is pretty fundamental and simple. So we would like to do that. Let's see how else we can do it. There actually is in the standard library a way of saying I want to initialize a vector with a sequence of elements. So I'll give it a sequence of elements. First I need to get myself a sequence of elements to give it. So I make here, take the sequence here, the values, I initialize a vector with it, I now make an array with it, and then I make a vector that takes this. And I wrote this slide to point out that this is indirect and verbose. I mean, do I get this right every time? Do you get that right every time? Probably not. And what I didn't notice when I first wrote this slide to illustrate the verbosity and the complexity was I actually made an error. I just truncated all my values, so it got the wrong values. If you have tedious, verbose, and indirect code, you make mistakes. You want direct expression of ideas so that you don't screw up so often. It's that simple. And furthermore, I violated one of the principles of design for C++. If you look at the design and evolution of C++, I have some design criteria for C++. Most of them has nothing to do with language technical details, but one of them says support user-defined and built-in types equally. And here, I can initialize this, my least favorite user-defined type, the array, with a list of elements. I can't do it to my most favorite container, which is vector. So I've supported built-in types better than user-defined types. So I now have to use arrays with all the possibilities of making mistakes that arrays comes with. So let's do it. We'll simply provide a mechanism that says, I want an initializer list. So that is a constructor that takes an initializer list. That's an initializer list. So when I do this, it'll call that constructor, and it can then construct it for me. Poof. You have an interaction here between the library, the standard initializer list, and the source code, so that you can say exactly what you want. And it works with vectors of all kinds. And furthermore, this mechanism works for any container that you can think of. If you don't like vectors but want lists or decks or your own favorite vector that works in your favorite environment, you can do it. As a matter of fact, it's a little more general than that. What we have actually designed here is a mechanism for having an initializer list match a function argument. So I can now say I have a function that takes an integer and initialize a list and another integer, and I can call it as I see it up there. So what I just got here is a way of initializing, of passing along a homogeneous list of elements of unknown length. In other words, we just got rid of 80% or so of all the uses of ... which is one of the type unsafe parts of C++, and it's also inefficient. So once you get sort of your shovel under something important, a lot of things happen. Now, one of the things people wanted out of this was a more uniform syntax. And since we are now starting to initialize with curly braces, we addressed the problem of there's too many ways of initializing things in C++. You can initialize with assignment syntax, you can initialize with parentheses. In some concepts, like when you make a new thing on the free store, you have to use the parentheses. In other places, you have to use curly braces and such. So, okay, let's define this so that curly braces work everywhere. So you can now write all of these things here, and it'll work. So I can initialize whatever type X is with a list like that. And once you get something uniform, you solve old problems. People have always complained that you could not initialize a vector that's a member from the constructor. Well, now you can. Now, I didn't particularly want to solve this problem because I think most users of arrays are brain dead. But once you get uniform solutions, you can't help solving problems. That's what universal means, or uniform means. So other things you can do, interestingly enough, if you have an x of a value a, it will result in the same value in all contexts. If you can try, you can try that in C++, use the assignment notation, use the parentheses notation, use the bracket notation, and you will find that not all places can use all of the variants, and the meanings get rather different. Here you'll get the same solution everywhere, and furthermore, it's always an initialization. I mean, this is really, it's a default initialization, right? Initialize with no value. It doesn't sort of magically turn into a function declaration the way it does with parentheses because of horrible old syntax. Here, this is definitely an initialization. This, you don't know what it is because I didn't tell you whether B was a type or a variable name. So all of these problems go away. So this is sort of the clean-up, tune-up kind of stuff, and it'll make a lot of difference to the surface of your code and probably make you use lists more often. And so this is good stuff. But let's get to the computer science part of it. Let's look at generic programming. This stuff with initializer lists helps a lot. Uniformity helps a lot with generic programming because generic programming relies critically on you writing code that works uniformly on a lot of different types. These a lot of different types has to have the same support, the same syntax, the same semantic things for different types. So uniformity is good. But let's go to the general. The fundamental cause of a lot of stuff in a lot of problems in C++ is that the compiler doesn't know what argument types are supposed to do. That is, if I have, say, an algorithm that takes an argument that's supposed to be a matrix of floating point numbers, a matrix of some floating type, I can't say that. It's just a type. And if I make a mistake, the error messages get spectacularly bad. It works beautifully for correct code, but you have to be very clever. If any of you have seen some of the Boost stuff, you don't want to be that clever. I mean, people are proud when they're clever. People are very proud when they understand the C declarator syntax. I mean, I'm slightly unusual there. When I finally figured out how the C declarator syntax worked, when I figured out how to write a function that could return a pointer to function without using a type def, I felt really stupid. That is, nobody should have to know this. This is not the normal reaction. People feel clever and want to show their friends and teach them too. So this stuff's too clever. It requires too much cleverness. You want to transform that into something that can be done automatically, correctly, simply, so that people can work on useful stuff rather than solving puzzles in the language. And the worst thing about the problems with templates in C++ is that the errors come too late. I mean, the standard example is I'm going to write a piece of code, and I'm going to use one of your algorithms, and I'm going to use a data structure I get from you, the type. Now, when you wrote your data structure, it has some sub-data structures. Of course, you have an algorithm that has some sub-algorithms. Now, I plug it together. And at link time, it's going to give an error message. It's going to give pages of error messages. It's mostly going to complain that some sub-data structure of yours that I'd never heard of gave indigestion to one of your sub-algorithms that I haven't heard about either. So they come late, they refer to implementation details I should never have to hear about. We have to solve this. Now, there's reasons why it's like that. One of the first rules of the game when you're improving something is don't break what works. So let's look at C++ templates and see what they're good at, so that we make sure we don't break it. There's no hierarchy required. This is really important. I mean, if I'm using your algorithm and your data structure, you've never heard of each other, the chance that your data structure fits into a hierarchy used by him is slim, unless you're in the same organization or things like that. If you want genuine reuse, you tend to not want the hierarchy. You don't want to modify the types to use an algorithm. And if you want 3 algorithms that has different requirements and a single type can meet them, you don't want to redefine that type 3 times to add the interfaces. Furthermore, templates handle built-in types beautifully. I really want a vector of integers. I don't want a vector of references to objects containing integers. Not even if they can hide this fact from me so I don't see it. The other thing that we found extremely useful, possibly even too useful, is to parameterize with both types and integers. This comes out of very simple use cases. Everything comes out of simple use cases. That's just simply the way I work and think. But the reason you need template parameters that are integers is you want to be able to have something like a buffer. It's a buffer of characters, and there's 1,028 of them. So you want to state the type of the elements and how many you have. This turns out to be really, really useful. One of the things that we found was that I aimed for generality, and template instantiation is Turing complete. This is you can do some cool things. One of the first ones was the famous prime number calculation at compile time. The only really hard thing these days is to get the output, which has to come in the error messages, and so you have to generate good error messages that comes out with, 2, 3, 5, 7. It can be done. It was done first time more than 10 years ago. And this stuff has become very popular when high performance is needed. So when you're doing a lot of linear algebra, when you're doing a lot of heavy-duty lookup, there's actually a lot of this stuff in there. I mean, when you do a Google search, you're not actually using C-level code. You're using template code. Whenever performance gets really important, you use this. And the reason is reasonably simple. What is a template? A template takes a couple of parameters, maintains all the information, gets it in one place so that you can munch it together and give it to the optimizers to generate good code. It simply allows you to merge information from different sources. That's useful. So we want to make sure that this isn't broken. And so what we built was basically a type system for C++ types, and for combinations of types, and for combinations of types and integers. I was looking for it since about 85 when I started working on templates, and I didn't find it. The section on templates in the design evolution of C++ starts with a 3-page apology for me not solving this problem. I mean, the problems that we have had didn't come as total surprise to me. I knew there was a problem. I just didn't know a solution. As far as I know, nobody else did either. Alex Stefanov, that did the STL, lobbied a lot. We've analyzed the stuff, and in the end, and here's the proof that this actually is hard and is computer science, we wrote a Pobl paper and an OOPSLA paper. You don't get a Pobl and an OOPSLA paper without being computer science. So this is seriously hard. And there's implementations. The one that you can download is by Doug Greger, Concept GCC. You can find, you can search and find it. And there's experimental versions of all the standard libraries. And by the way the committee works is a lot through reflector emails and such electronically. Then we meet, and when we meet in subgroups, and sometimes a subgroup meets at separate meetings. That's one of the subgroups working on concepts there. That was at Google this February. Let's see. So what do we want to do? Again, back to the fundamental, what we always want to do with C++, direct expression of intent. So if I'm writing a piece of algorithm thing that wants something that can be used as a matrix of something that behaves like floating point numbers, that's what I want to say. And we would like to, when we state our things, we would like to separate implementation and use. In other words, we want to have proper interfaces, but that's a little bit hard to do when the purpose of the exercise is at compile time to merge a lot of information together to get optimal performance. So in particular, we don't want to have, well, I'll get to what we don't want to have, but hierarchies and dynamic lookup is high on the list. We want increased expressiveness because when you are doing generic programming, you want uniformity, and that means that you want, and then we take another type called value and we use them. Here we say, what kind of types? Well, I want a forward iterator. A forward iterator is where we can go along and touch one element after the other. And we want a value type. A value type is something you can copy. And then we want to require that what the forward iterator points to is a type that can accept the value that's coming in. That's what we said. And so everything's set there. So what is the first thing we do when we get a fancy new toy? We try and see if we can break it. So here we're trying to do one of the things that gives bad error messages on current compilers. We take two integers, it's the same type, so we can fool the old mechanism, and 99, but no, not this. It says, well, you know, int is not a forward iterator, and it'll actually say it's not a forward iterator because it doesn't have a star, a unary dereference operator. Okay, so we can't fool it, which is good. And note, there was no implementation there. This is a declaration, so it's done just with the interface. We're helping the users a lot here, and we check, we try with an array, and you know it works because an int star is a forward iterator and everything is fine. And then we clog it and make sure that we haven't gotten an overhead at runtime. Last time somebody clocked this and reported back to me, there actually was an overhead of about 3%. We'll get rid of it. That's not good enough. But this basically works. So now we have helped most people, they're the users. But we haven't helped ourselves and others when we're the implementers. There's another set of errors that are really nasty. Here is a fairly standard, obvious, reasonable implementation. We go till we hit the end, bung in the value, go to the next element. This is plausible, but it's not correct. Because a forward iterator is something you can go next, 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 next. It's something like an input stream or a list. It's not a random access iterator like an array or a vector where you can just go over there, go n steps forward. Now the type system doesn't know that 1 is a very special number and just means the next. So what it will do now, it'll say, oh sorry guys, you can't add an integer to a forward iterator. Basically, it will not tell you go get a random iterator, but that's what you will know soon enough. Basically, use the operation that's available for the forward iterator, and it'll work. Now, this is important because when we build stuff, it's quite hard to test code that is that general. If I'd written this code without concepts, with standard C++ 98 templates, I could have tested it with arrays, I could have tested it with vectors, and it all have worked. And if I had been naive or sloppy or something, I would then have shipped my code to you. And it'll have worked with your vectors, and then someday you, or one of your users, will instantiate it with a list, and it'll go boom. We're back in the problem we're trying to solve. Anyway, here we can handle uses and get good error messages, and we can handle implementations, get good error messages. Okay, let's go on. Expressiveness. One of the things that we are doing wrong in templates today is we have to say too much. So let's see how we can simplify it. One of the ways you can simplify it is provide versions that are simpler. So I want to sort a vector, I want to sort a vector with a function object, sort a list with a function object, sort a vector with the sequence of elements, da 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 da. You can do this today. It's been done. Matt Austin did it for the SGI implementation of the standard library. But it's a mess of helper function and traits. It's one of these things where you realize that Matt is a very clever guy. And you shouldn't have to know that. You can see the skeleton to get the scaffolding to get this work. So what we will do with concepts, we will simply say, if you give me 2 random iterators, you do it this way. If you give me 2 sort of random access iterators and a comparison object, we'll just check that the comparison object can compare the right things and give you that. And if we get a container, well, we'll use the container version, which is to grab the iterators and use the other one, and so on. This is sort of what we learned, not quite in kindergarten, but we certainly learned it the first year we wrote code. We can use the types of our type system to ease our job with better and get better error messages. That's just what we're doing with concepts. Performance, it works. There's one problem with performance that goes beyond the sort of the language technical thing of getting the primitive operations to work reasonably fast. And this is sort of the algorithmic thing. We found that very pleasant with templates and a bit surprising to some people. So a lot of algorithms sort of walk through data structures. In particular, they sort of go to the middle and they do the first half and the second half and that kind of stuff. So there's an operation called advance for going over there. And it comes in 2 flavors. If you have a random access iterator like a vector, you just go over there. If you have a forward iterator or bidirectional iterator, you can't just go over there. You have to go over there by going through all the intermediate steps. Much slower, you touch a lot of memory, which is bad on modern computers, and all of that kind of stuff. So, here I'm writing a sort of a naive operation, and I'm doing it with forward iterators so that it works for all containers, for all cases roughly. And I'm doing the obvious thing. I'm going to the middle, and then I'm going to do something. If you look at the standard library, lots of algorithms have this general structure. If you go to look in your algorithms textbook, a lot of the algorithms have this structure. Now, the only problem is traditional programming languages are saying you're advancing a forward iterator. We'll pick the forward iterator, and we'll go slowly through. And a lot of your algorithms have now turned from linear algorithms square in complexity. Because instead of just going over there, for each step you sort of do that. Now, currently with templates, it'll simply go and look what iterator you really have and pick the right one. And we have to get that to work, and we did. So we have a vector of integers, and we call it this algorithm with the vectors begin and for, and it will go, and at the first level of compile time, it'll say, yeah, I can do this. I've got a forward iterator. It'll work. But when it comes to code generation, it'll say, well, I know I can generate code because there is a forward iterator. But let me just see, what is it really? Oh, it's really a random access iterator. I can go the fast way. And this works. This is, if you're into type theory, is what breaks system F and makes modular type checking impossible and makes these things run really fast. We're doing it. Now, if any of you were really on the ball or had read this before, you would have noticed I said that an integer was a forward iterator, and I was several times referring to a forward iterator's value type. Now, an int star doesn't have any member called value type. I mean, don't have any members anyway. They weren't invented when pointers were invented. So how can we get int star to be a forward iterator? In other words, how can we get int star to have a value type? And the answer is we can say, when you are looking at a forward iterator that is a T star pretend that T is the value type. It's sort of like a pair of glasses you put on. Now you see not just what it is, but what your glasses help you to see. And so that's what that concept map is doing. It maps the maps between the sort of raw type, the T star view, and the input iterator view. So that allows us to adapt the int star 30-year-old kind of technology into the new stuff. This is a very useful, oops. Okay. That's a very useful technique for combining stuff from different sources. I mentioned before that if you had written a code and you have an algorithm, the chance that they match is low. But it turns out that the chance that they almost match is pretty high. And so you use these maps to sort of fit things together. Now, let me just give a quick summary of this kind of stuff. The first up there is a template alias. It does what some people have been trying to call template type def, and they didn't work. Basically, I want to say I want something called vec. That is a synonym for standard vector of T and my allocator of T. In other words, I want to take a template and bind one of the arguments, currently. And so I can do that. That's an alias declaration. And then I can use it down on the next list. So I make a vec of double with that initializer list. Just make the code prettier, work. And then the real magic is, of course, the innocent-looking sort of V, which requires concepts and type checking and overloading, and the whole works. And then there's other things to help. I can't get into details here, but notice that when we write a loop with a standard library, we very often start from the beginning, go to the end, all of that. But to get the beginning, we need to define the loop variable, and we have to give the type. And so in this case, we would have to remember, in C++ 98, we would have to remember that V was a vector of double with my allocator of double, and then colon, colon, iterator. That's verbose, and it's unnecessary, and it's complicated. Now, I really like that use of auto, which says, it means the type is what you get from your initializer. Very simple. I first implemented that in 1982 or 83 and was forced to take it out again because of C incompatibilities. Then we fixed the incompatibility in both C and C++, and now I can get it back. Bit late, but better late than never. And there's also another loop construct in there that'll work for any ranges. In particular, it'll work for a vector which defines a range. So I say for all x in V, I'm going to do this, and the access is going to be const so that I don't modify it, and ref so I don't copy it. So there's an extra loop. Okay, so there's a lot of features here which I'll come back to. So will this happen? I mean, what I have been saying is not quite science fiction, but you can't go down to Best Buy or whatever you have around here and buy it. It's not science fiction. It's been designed. Everything here is implemented by somebody somewhere. Nothing exists that can do all of these things put together. We adopted a schedule a couple of years ago. We are trying to keep to it. There's lots of battles in Toronto right now about whether we can meet this schedule. And I still would like to see C++ 0x to become C++ 09 and not any other number. But we'll see. And I'll put some list of features up to help the question and answer session. But your questions are not limited to C++ 0x. Okay, questions? Yes?
In your opinion, what's your opinion about the Microsoft implementation of C++, say, inside of Visual C++?
I'm repeating because of the recording and such. What's my opinion about Microsoft's implementation of C++? It's one of the best implementations there are, and it's quite conforming, and you can write good portable code with it. The same is true for essentially all of the EDD-based compilers, and GCC is quite good also. Microsoft generates rather good code, which is also good. Now, that was a good thing, and this was not true a few years ago, but it's true now. They, of course, really don't want you to write in ISO standard C++. They want you to write in their managed dialect of C++ known as C++/CLI. And if you do that, you get some nice facilities, nice integration, and you will never run on anything but Vista. Now, let me point out that Microsoft is not the only one that plays that game. Apple has a very nice implementation of C++. It's a variant of the GNU one, and they really, really want you to use their GUI facility, which happens to be in their very own proprietary Objective C++ dialect. And GNU does it too. So let's remember to spread the blame out fairly equally. Microsoft is a bigger problem because they have more users, and after them comes GNU, because they've got lots of users, but they're all playing that game. These days, the compiler is actually fairly good in a lot of cases. If you stay out of the low-end embedded systems, you can write fairly good portable code across a lot of platforms. This was not true 5 years ago.
You talked about the challenges of revising such a popular language. It's got to be a lot of hard work. Do you ever think you'll design a new language from scratch?
Do I ever think in design a new language from scratch? I don't think so, certainly not from scratch. It's very tempting to write a new language, but you have to answer the question, why are you designing a language? A lot of people design a language to get a PhD or to get tenure or to become stinking rich by that. And I think they're all good answers for the individuals, but my favorite answer is you design a language to solve a problem or to solve a range of problems. That's what I did last time. I had some problems, and to the best of my knowledge, even today, at the time no language existed that could do what I wanted. I wanted to do similar style programming, object-oriented programming, for hardcore systems programming with really good efficiency and access to the hardware. It didn't exist. So if I'm going to do something, it will be because there's a problem that I feel that needs solving. Even then, I'm likely to somehow or other stay very close to a language, because the advantage of not starting from scratch is immense in terms of tools, infrastructure, teaching, and you get compatibility problems forever after. But just starting from the beginning is hard. Yes?
So what about parallelism? You mentioned threads. There's also atomic transactions and things like cache management.
One of the major challenges today is concurrency. Basically, the machine architects have run out of steam because they can't make their machines run faster. And they have all of these nice chips that the nice transistors that Moore's laws give us, and they want to use them for something. And so they use them for more and more processes. So concurrency in many forms become extremely important. So the question is, how do you do that? My favorite answer is you provide a set of primitives, and on top of those primitives you build libraries that are geared to a particular model of concurrency. So you get things like the Intel concurrency components, a library, I've forgotten what it's called, Arch Robinson stuff, or the stable from Lawrence Strauswerker at Texas A&M where I am. And basically you build a library that supports the model. The worst way of doing things is to say, give me a couple of threads and then I'll build my own locked containers. And basically, I'm cleverer than all of these guys, so I'm not going to get their performance on logical problems. Yes, you are. If you're going to write anything trivial straight from threads and with your own locks, you're either going to deadlock or you're going to get data races. It's just too hard to get right. But you need, so my favored solution is to provide primitives, which we're trying to do in the C++ OX standard, and then provide high-level libraries that allows you to actually efficiently use that concurrency. Doing it directly is too hard. I'm very sad that we don't get very good higher-level libraries in the C++ standard library. It looks as if we're going to get thread pools and futures. That basically means that I can give you a task to do, and you're in charge of a bunch of threads. And when you're finished, you give me back my answer. I can wait for the answer on that. That's it. The other thing I would have liked was a simple message queue. I'm unlikely to get it. We're not going to get far enough from the hardware in the standard, so there's an opening for others. Yes?
How long after the standard is finalized do you expect to see a production level compiler?
How long after the standard is out do I expect to see a production quality compiler? Last time the vendors started to put in features before the standard was finished. Some of them got burnt, and a lot of us got burnt in the sense that different compilers provided different subsets. I think this time everybody's going to wait a bit longer, but they've already started. So the long ISO process means, for instance, that feature complete happens about 2 years before the standard is out. I mean, if I get my way and I'm really lucky, October the 6th, we will have a first draft with all the features, and if I'm wrong, I think it'll be in the late winter. And a year and a half to 2 years later, we'll have a standard after a lot of revision work and such. And my guess is that the compilers will start coming very soon after that, because the implementers already have some of the features there. Let me just see here. I don't know if anybody has the improved enumerations implemented. Everything else, I know somebody who's got an implementation. So things are happening. Yes?
So is Auto like a type inference engine?
Auto is sort of type inference, but it's very simple. You simply look at the variable being, at the initializer, see what the type is, and that's the type you get. So that's the most trivial. Where you really get fairly serious type inference is actually in the template instantiation. Let's see, that's roughly equivalent in power for the type inference in ML. Yes?
Would it be useful to have a standardized switch in each compiler which enables deprecated, or which deprecates features for in the new version of the language, even in the live teaching?
Would it be useful to have a switch in every compiler for deprecating features? Yes, that would be useful, because the compilers has to support old features we'd like to get rid of forever and deprecated features, but it would be nice if there was a switch for it. I have not been able to convince the compiler vendors to do that, and especially not in any consistent way.
There's been some talk about bringing garbage collection into the language. We saw that Sun, quote-unquote, solved this in Java by moving all user-defined types to the stack. Is there really a way to bring garbage collection into C++ without basically treating it like a construct like boost shared pointer at every point?
Yes, it is possible to do garbage collection in C++. It is possible to do without putting all the stuff over on the free store and access everything indirectly. An implementation exists. The first thing I'm going to do tomorrow morning is to sit through several hours of discussion of whether it will become a standard. It looked like it was going to become a standard next year, but there's a lot of resistance now. So we can do it efficiently, but there's two problems that gives a lot of discussion. The first problem is leakage of non-memory resources. What we do in C++ is to rely a lot on sort of various forms of scoped handles for things to automatically free sockets, file handles, thread handles, and things like that. And when we don't have a well-determined scope for a resource, we use a smart pointer, or we have to be all clever coding. But the point is that we have actually got a pretty good handle on resource management in C++, much better than they have in Java and C#. One of the ways that has been done is people have done measurements on how long a resource is retained in various languages. And for instance, C++ tends to retain its resources about half the time of C# for equivalent applications. This has been measured for fairly large sets of applications. So there's something right about what we're doing. And there's people that claims that if we get a garbage collector, people will become so sloppy about their coding styles that the performance will become, the resource retention will be as poor as in other languages. And again, C++ has a core application area which is fairly close to the hardware and fairly closely managed resources. The other problem that you get with garbage collection is that garbage collection can be a performance virus. The worst example I can think of is think about me having a very carefully tuned program that does something, taking great care of its memory, running high performance in about 4 gig. Very serious program. There's lots of them. Now, I have a component, say a GUI library, that uses garbage collection. If you're doing GUI, garbage collection is quite convenient. There's no really scopes to help you and such. Now you drop a nicely tested GUI component down into the highly tuned library. The GUI has been measured, it works fine, there's no delays that you can, as a human, see. When you dropped it down into the big application, the heap grew by a factor of 20. That meant that the garbage collections now took 20 times longer. That means that your nice GUI library is now running in Treacle, and your high-performance application is no longer a high-performance application. Solving problems like that is really hard. Furthermore, there's other things. When you run with a garbage collector, a moving garbage collector, it really works better if you've got twice as much memory than you ever need. And a lot of C++ code runs in all the memory there is. I mean, I was first measured some of my code against some Lisp code, and they thought it was really unfair that I claimed I ran 12 times faster because my program didn't swap, and it wasn't a language difference, it was just a swapping cost. And I smiled sweetly and says, I don't swap because I don't run out of memory. That's fair. So there's a very lively debate about garbage collection. It's the first thing I'm going to do tomorrow morning. If you go to the WG21 site, you can see the current design. It's by Mike Spertus and Hans-Jürgen Böhm. Look up those names on the list of papers and you'll find all the details. Yes?
a lot of academic institutions have dropped teaching C++ in different respects. Waterloo keeps that up, but there are certain universities that are dropping it altogether, leaving it as an exercise for the student. And as a result, there are a lot of poor coding practices and poor coding solutions coming in for people. Are there any plans to at least have some documentation on how it can be more teachable as a language?
So yeah, there's unfortunately a lot of universities that are dropping C++. There's also a number of universities that are actually increasing the teaching, and there's a lot of use of C++ in the upper level courses and and the graduate courses, but you're right, people have really weird ideas about what good code looks like. Personally, when I became an academic a couple of years ago, somebody talked me into starting to teach some undergrads. So I have been teaching freshmen programming at Texas A&M, and that's an interesting exercise. I'm more used to serious PhDs from good universities with 10 years of experience, and it's not quite the same. And so I found out how I wanted to teach it. I tried out the ideas, and I have basically written a textbook which, if I can get my act together, will appear sometime next year. And so that will be a rather different textbook for beginners. I've never written a textbook for beginners because I didn't know beginners. And you should not try and do what you don't know. So that'll become available. I think that'll help a lot of places that teach C++. Yeah.
So you implemented C++ sort of originally in the mid-'80s. How soon after that did you start to see C++ sort of taking over as the primary language?
So I designed and implemented C++ over the early 80s, and the first commercial release was in 85, and I could keep track of the number of users for the 80s. Basically, I knew all the implementers and everybody has shipped compilers, and I could ask them, and I could collaborate my data by seeing how many textbooks were sold. And I had more access to data than anybody, so I had good data. In the period from 1979, when there was one user, till 1991, the doubling rate was 7.5 months. So we have this, and then there's the curve doing that now. It's going slower, but we're up at 3 million. Basically, I was too busy to notice. I mean, much of this, yeah, it's great, we've got some more users. Yeah, it's great, hurry, we have to fix things. And that went on for about 10 years till I got a breather. But it was always sort of, oh, the user population doubled again. And then that was a decade of that. Yes?
Right now, a lot of templated classes generally use template hoisting to make them slightly more efficient in terms of code size at compilation time. Is anything being done to address the issues that make that necessary?
What do you mean template hoisting?
Basically having a void, like a base class. Say you had a vector, a templated vector. You have a base class that operates on void pointers.
Yeah, well, so there's a trick of avoiding a lot of separate instantiations by having a common implementation based on a void star. I don't see any serious change in that. If you want to eliminate the number of instantiations, that's a good portable technique for doing that. There exist compilers that can actually deduce that all your instantiations are pointers, and then avoid what you call hoisting, that is doing it themselves inside the compiler. The problem is that only the compilers that can do that will do it, and your code now is portable, but not the performance of your code is not portable. So I care a lot about portability, and that includes portability of performance. And so it'll be a while before I stop using that trick, which is one of my original ones, by the way. Yes?
What's your opinion of generic programming at the runtime level? Languages like Objective-C?
What's my opinion on generic programming at the runtime level? I think it would be a good idea, but most of what's called generic programming at the runtime level either have so many indirections that it runs at about 1/10 of the speed of non-generic code, or it is not what I would call generic, that it is very limited genericity, and you can't do any of the interesting stuff. So I think it would be a good idea, but somebody has to define generic programming properly and implement it properly. There's a couple of competing definitions of generic programming. The one I'm using is the one that comes from, notably, Alex Stefanoff and to some extent Mossa, which the idea of hoisting an algorithm from an efficient, concrete version through increasingly general versions with decreasing set of constraints without losing the original efficiency. So performance is part of my concept of generic programming. There are things you can do elegantly if you throw away 90% of your performance. They're very interesting. They're useful enough for a lot of people, but it's not the game I'm in. So I'm following that school of thought where generic programming should also be comparable or equal or improved efficiency compared to the non-generic form.
You talked about sort of trying to make sure there wasn't any difference in using user-defined types and built-in types. And one of the places where the seems to come up a fair bit is pointers, because there's a lot of optimizations for when you're doing with pointers, like overloaded functions that deal with pointers that it selects the most derived one you pass a pointer to, and it's hard to emulate that if you're doing smart pointers. And it seems to me it's the same sort of thing. Is that, do you see it as a problem you're trying to work on?
Okay, first of all, I think smart pointers are overused. They're a temptation. I'll get back to that. Secondly, we can emulate inheritance with smart pointers. That is no longer a problem, even in C++ 98. In C++ OX, we can do initialization of those things better and such. So you can basically build a perfect smart pointer now. And the reason I worry about smart pointers is that, for instance, if you use a smart pointer of the usual type where you use it for sharing, now, if I have a smart pointer and I give you a copy, now, if we don't have a contract between us on how it's used, we've got a race condition. I mean, there's no lock on this thing, and we have two pieces of code that pokes in the same area. And you can get a lot of traditional pointer problems. The only one you don't get is the problem of accessing an invalid pointer. So you have to be very careful what is the semantics of this so-called smart pointer you're dealing with. So we're going to get in the next standard a unique pointer, which is an auto pointer without the problems, and we're going to get a counted pointer that does the sharing. But careful with them; they're easy to overuse. Yes.
With templates, there's a lot of sort of interesting parallels between them and duck typing, which are used in dynamic languages. The difference, of course, being that they're static and determinate compile time. Because concepts provide a more robust system for checking templates, do you think that perhaps concepts are kind of going to overtake classes in terms of defining object contracts?
So the question is, will templates overtake classes for writing code and for having contracts? And duck typing was mentioned. Yes, templates has roughly the same as what they call duck typing in the scripting languages, and it's done dynamically. I think that the interfaces will be much better specified with concepts, but there's still a large component of what we can call duck typing in it. That is, if it has a plus, you can add it. If it has a plus plus, you can increment it. Now, you can have two flavors, one where you explicitly define what matches what. It is still not intrusive. That is, if you have a type and he has an algorithm that requires certain things, and actually he can require that you explicitly say that you meet his interface, then you just write, when you learn about his algorithm, you just write the statement that says my type will work with his, and the compiler checks it. It's still sort of duck typing, but you have a control. You also have different concepts called automatic concepts, where it simply does it for you. But yes, templates are getting very important, and they're getting more important because they will get improved by C++ 03. But I'll give you an example of how much they can take over in certain environments. And that's an older example. Templates has the interesting property that if you don't use a member function of a class, no code will be generated for it. So if you now have a class with 5 functions and you only use 3, 2 of them will never get laid down. You also have embedded systems and safety critical areas that has as a rule that no untested code, no dead code may be shipped. Now if you take your classes and make them into templates, only the function you use are laid down, so you just met the no dead code rule. So templates are actually being used in preference to classes, of course in combination with classes, it's a template class, to get better memory footprints in embedded systems. These things turn up in the strangest places. And please do remember, templates by themselves is absolutely nothing. They help you to abstract over something. And what you need, you start abstracting over the built-in types, but it doesn't really get interesting till you get some classes into the game so that you can abstract over built-in types and classes and all the kind of good stuff. Templates is, by themselves is nothing. Yes?
Have you ever gotten any death threats because of changes you've made to the language?
I have never gotten any death threats for any reason. And let's keep it that way. Yes?
Are there any particular, I guess, naming conventions that you subscribe to in general, like camel notation or Hungarian?
Is there any particular naming conventions I ascribe to? Yeah, I like underscores. I do not like the camel stuff. It's unreadable, and I think it has been proven to be less readable than underscores many times. Some people think it's cute. I think they've been hoodwinked.
With the new language features that you come up with, since there's so many languages that are new and upcoming right now, do you try to reuse any of the sort of good things that they've done whenever you try to make these standards? Or do you just...
I try to learn from new languages, in particular uses of new languages. But grafting a feature from one language to another is much harder than people usually think. So it is more that you see something work in one language, then you see what problem are they solving. Can we solve the same problem as elegantly in C++? If the answer is no, we look how we can improve it and what you can learn from the way it was done in the other language. But simple grafting is a very hard exercise. Yes?
Today, with the standard, C++ is very specified, very rigorously specified. When you initially designed the language, did you start from the very beginning with rigorous specifications, or how did that process develop?
So we're trying to be rigorous, but it's still informal in the sense that it's written in English. And I tried to be as rigorous as I could and informal because it was written in English. And I started out with the specification of C written by Dennis Ritchie. Some things have improved since then, and some things have just become more obscure because of the more words people use. We have tried several times to see if we could also make it formal. It would be nice to have a formal semantics, either for the whole thing or for part of it, and this has not been all that successful over the years. But I'm very glad to report that this year a group at IBM managed to prove that the C++ inheritance system was formally sound. It's proven. So 20 years later, they proved that I didn't screw up. Now, this is really nice, especially, of course, because that was not what they were trying to prove. Yes?
With the widespread Java things in the embedded world, and Sun is going to release some hardware that runs Java bytecode natively, are you afraid that C++ is going to be moved away from
Let's see, Java would kill C++ totally in 2 years, they said in '96. And they've been sort of repeating this story over and over again. There's a lot of Java, and there's a lot of C++, and it's a big world. And live and let live. I know it's not the Java philosophy, but it's mine. Maybe I should give people a chance to escape if that's it. So, last question.
You talk a lot about performance and embedded systems. And a lot of these features that are already in the language and that are coming up are really compile time things that optimize away and like to get faster code. But then you also have features like runtime typing and exceptions, which kind of tend to slow down the code. So what are your opinions on the future of these types of features?
I mean, you have to have a balance. If you need something at runtime, you need something at runtime. I mean, most of the good uses of virtual functions simply can't be done at compile time because you don't have the information. Similarly, exceptions are excellent for getting out of a context and for structuring your code. And you can write compilers, and people do it regularly, where the cost of an exception is 0 unless you actually throw it. And since they're going to be exceptional, your main line of code will run maximally fast, and your error handling gets slowed down a little bit by the error path. So there's trade-offs, and some things you just have to do at runtime. Thank you.